let's take a look at these things we call asymptotes. Basically, they're a geometrical way of describing out at the extremities of a function. Right? What's happening out at infinity and minus infinity. And I've just drawn a random curve here, which I've tried to capture as many different types of asymptotes that I can. So here's the different types. Vertical asymptotes, possibly the first type of asymptote we encounter. And we have one there at A. So this is happening out of the extremity, but it's the extremities of the y, so it's the answer that's infinity or minus infinity. So what we're saying is, look, as that x value is getting closer and closer to a value of A, the answer, the function value, the y value, is getting closer and closer to being out at the extremity, infinity or minus infinity. So there's a vertical asymptote, and one thing we know is functions will never ever cut or touch it because it's an exclusion in the domain. So it's impossible to plot a point there because that point is excluded from the domain. We also have horizontal ones, and there's one there at B. Also at the extremity, but this time it's how the x values are going to infinity. So our limit would be as x is approaching plus or minus infinity, and in this case we have at B. Well, actually the reality is that's probably wrong what I wrote down. The limit as x approaches positive infinity, it's approaching B. It certainly is not happening out at negative infinity. There's nothing to say that both extremities have to be the same. It happens a lot, like our basic hyperbola there, they're both approaching 0 out of the extremities, but it doesn't have to. It doesn't have to. And then we have oblique ones, and here's an oblique one here, and that's actually telling me what's happening out at negative infinity for this picture. But that's when it's still going to infinity, but it's not going horizontally, it's going off at an angle. So both of them are going to infinity or minus infinity if you like. So this one, as the x value is going to minus infinity, the y value is going to plus infinity. So that creates an oblique asymptote. In fact, asymptotes don't actually have to be straight lines. You could have a parabolic asymptote. It just means that as we're getting closer and closer to infinity, this function is closer and closer to being that quadratic. It's approaching that quadratic. So it could take on that shape. It looks like it's taking on that shape at the extremities. And the thing with these ones is, and you'll notice it did here in our example, it is possible to cut or touch the horizontal or oblique asymptotes. Because remember, they are just describing what's happening out of the extremities. So if it's not out of the extremities, those asymptotes are totally irrelevant to the picture. So it can cut them. Now, it might not, but it is possible for them to do it. The asymptotes are dotted because we're saying it's not actually part of the curve. It's just telling us what's happening out at the extremities. So we dot it. The most basic one we see with asymptotes is what we call the rectangular hyperbolic function. And there it is in all its glory. Y equals 1 on x, or sometimes you'll see it as x times y is equal to 1. Now, any data, when you plot data, if it demonstrates inverse variation, so it's proportional to the reciprocal, 1 over, then that will create a rectangular hyperbola. Now, why do we call it a rectangular hyperbola? Well, the asymptotes are perpendicular to each other, so they're rectangular. That's where it gets its name from. You might not have ever heard it called the rectangular hyperbola before. You just heard hyperbola. But you see, there are other hyperbolas as well that aren't rectangular. No, this is a rectangular hyperbola. And all rectangular hyperbolas can be transformed using translations, all different types of translations. Recognizing the hyperbolic function then. So y equals 1 on x. Well, one variable is going to be in the numerator. One's probably going to be in the denominator because that's going to create the asymptote, that problem we've got. So that's the sort of thing I'm looking for. If I see that, I'm thinking, okay, I've got some sort of hyperbolic shape. Exponentials also have asymptotes. So the orientation is determined by the base. When the base is bigger than 1, and the base is bigger than 1. So it starts shallow and then gets steep very, very quickly. The exponential just takes off, like so. If the base is in between 0 and 1, then it's the flip of that. It does the other thing. It starts steep and then becomes shallow. You don't have exponentials where the base is negative, because if you were to plot or attempt to plot it, you're just going to get a chaotic set of points, because you can't find square root of a negative number, for instance, so you couldn't raise it to the power of a half or a quarter or anything like that. So there'd be all these exclusions, so you end up with a set of points which is just chaotic. It doesn't make sense. It also means that if the power is negative, the reverse will change, because if you think about it, if the base is less than 1, it's like saying a half to the power of x. Well, a half to the power of x is the same as saying 2 to the power of negative x. Often call that one the backwards exponential, because it's backwards. That's just my name, by the way, it's not an official name. How do you recognise it? Well, this one's kind of easy to recognise, because you go, oh look, one of the variables is in the power. And of course another name for a power is the exponent, and that's where it gets its name from, the exponential, because it's in the exponent. Base is always positive, not equal to 1 as well. I mean, it's one of those questions. Is 1 to the power of x an exponential? I mean, 1 to the power of anything is 1, so really it's just this horizontal line. Is it fair to call it an exponential? I say no, but anyway, we could probably debate about that all day. Alright, so it's 3h. We'll now add some asymptote questions in there.